Good morning, everyone. Boy, this is a pretty slim class today. Okay, we got a couple more people joining us. Okay, we'll just wait. There's one other person that is just connecting, so we'll just give them a second to actually connect. And it looks like they're having some issues connecting. Okay, so it looks like everyone who is going to join us has connected. As I just mentioned, doesn't look like too many of us could get up for this nice and early Friday morning class. So before I get going, I just want to point out that I did place a rubric into DC Connect, into the assignment section. So there's now a rubric there indicating how the marking will work for the video presentations that are going to take place on November 25th and 26th. And as Aaron said, the dedicated few are here today. Well, we still have some people connecting, so hopefully more people will join us as we move through. So as I said, there's a rubric there now for the video presentation. Does anyone have any questions about the video presentation before we get going? No. One of the things I want to mention to you that you guys do have those student quality feedback surveys. They were sent to you directly by the college yesterday. We do get notified. It's just a brief notification that just says how many have came back, and I noticed that some people have sent them back, but not too many. So you only have till I believe it's November 24th to complete these and send them back into the college. So I would encourage you to get them completed and get them shipped back. Okay, tomorrow. See, it's too early on a Friday morning. So for today, what I wanted to do is we're actually progressing quite well through the course material. We do have, these 2 days of presentations that are going to take place towards the end of November, and then on December 3rd we're going to have a guest speaker. But even with them, we are progressing well. We're a bit ahead of schedule. So what I wanted to do is I wanted to take to do an actual case study with you guys of an actual facility and the so take a look at an actual facility, the types of wastes that they're reporting, how those wastes are classified for disposal purposes, and how the calculations are done for reporting of releases to the National Pollutant Release Inventory. So I know you guys are all very enthusiastic about math and probably are quite disappointed that we haven't seen any math so far in these lectures. So we will touch on a bit of the math that gets done typically by consultants or by plant environmental people in order to quantify releases and then report them to the Ministry of the Environment. What I'm also going to be using for the first time this morning is a pad, a Wacom pad with a whiteboard in order to do some drawings. So I'll be using that for the first time. So we'll see how that works out. I did practice last night. and it did seem to work quite well. So hopefully we won't have any technical issues with that. So what I am going to do, actually, there's a couple of things I'm going to do first. Essentially, we are going to be using today in this case study the Ontario Ministry of the Environment Waste Generator Guidance Manual. So I just sent you I just sent you a link to the guidance manual so that you can actually open it if you want to follow along on your screen. But essentially what we'll be using is figure 3 out of the guidance manual. That's where facilities go directly to characterize their wastes. And Matthew just said we get to see Stuart the artist, and I think Matthew's going to be awful disappointed because art was not one of my strong points at any point in time in my life. Okay, so I just shared that link with you guys. Okay, now what I'm going to do is I'm going to share my screen. There's going to be a fair bit of screen sharing today, so hopefully that goes well for us. So you guys can now see my PowerPoint, and I'm going to start this slideshow from the beginning so we can see these slides full size, right? So today, as I meant, this is so frustrating because these yep, they all have somebody speaking over the slide. So we'll just go back to showing them this way without the annotation. Okay, so as I said, case study for waste classification and regulatory reporting. That's what we're going to take a look at today. I anticipate that this is going to take us pretty well the full 2 hours to do this, to walk through this with this process. Okay, so essentially an overview is the case study. We'll look at how waste is generated from an actual industrial process, the characterization of industrial waste streams under Ontario Regulation 347. So we're going to look at the wastes that are generated from this process, and then we're going to go to figure 3 of the waste generator guidance manual, and we're going to determine if these wastes are regulated under Regulation 347 or if they can be disposed of under or if they can be disposed of outside of Regulation 347 or essentially as a non-hazardous waste. And then we're going to look at the calculations required for reporting of releases to the National Pollutant Release Inventory. Okay, we've done a lot of work over the last weeks where we've looked at the HWIN database and we've looked at the MPRI reports for various facilities, and we've tried to make some connection between the two, the HWIN database and the MPRI. And probably what you've noticed from this process is it's very difficult to directly connect the HWIN, what's been reported under HWIN, as to what is reported under the National Pollutant Release Inventory. So I'm hoping as we go through this, it'll become clear to you guys why that is, why there's different amounts reported to the two different databases. Okay. The learning objectives will be how to characterize waste using the Ontario Waste Generators Guidance Manual, and how industrial releases are calculated for reporting to the National Pollutant Release Inventory. So at the end of this case study, you guys should essentially at least understand how wastes are characterized by facilities before they're shipped. And that is a very important process to go through, because if the wastes are improperly characterized, you can end up in a situation where the facility is non-compliant with their waste disposal requirements. And how industrial releases are calculated. This will give you guys an actual example of the actual calculation process that industries have to go through in order to accurately quantify their releases to the MPRI. And I say accurately quantify your releases. The National Pollutant Release Inventory, you're supposed to be reporting the actual releases that the facility had in the previous calendar year, and that information becomes publicly available. So facilities don't want to overestimate the releases, but at the same time, they are legally required to report accurately. So they need to be sure that they're not underreporting their releases. Okay, so case study. Metal inert gas or MIG welding wire manufacturing. So this is actually relates to an actual client that we have, and we have done their waste characterization and their MPRI reporting for them for the last 20 years. So yeah, looks like Aaron actually managed to figure out who this company what this company is. So as I said, the company is a large-scale manufacturer of metal inert gas or MIG welding wire. MIG welding, for those of you who are unfamiliar with the welding process, MIG welding is an arc welding process in which a continuous solid wire electrode is fed through a welding gun and into a weld pool, joining the two metal base pieces together. A shield gas is also used through the welding gun and protects the weld pool from contamination. So metal inert gas, the inert gas is typically nitrogen, and that is what is used as the shielding gas. And the metal is generally the two pieces of metal that you want to join together in conjunction with the metal welding electrode. That definition comes right from the Miller Welding website. The link to their website is shown below. Okay, so the main manufacturing processes at the site include the receiving of raw steel, shot blasting of the raw steel wire to remove mill scale, drawing of the wire to the appropriate size, and the application of a copper coating to the wire. Now, I have a question for you guys. Have any of you ever put together a process flow chart or a process flow diagram? I can't see all your screens, but yeah, so it looks like you guys are at least familiar with process flow charts. We spend a large portion of our time drawing process flow charts. We have to do it for any application for a permit that goes to the Ministry of the Environment. We have to include a process flow chart. So for those of you who are going to be working in the field as chemical engineering technologists or environmental people within plants, you're going to have to get used to creating these process flow charts. And if not actually creating them yourself, learning how to use them. There are process flow charts can be put together for many reasons. We put them together as visual representations of processes, so that people who are sitting in government offices can look at those process flow charts and get an understanding of how the process actually works, and where within the process there will be various emissions that would come from that process. So this is where we're going to attempt for the first time to use this drawing pad, and this is where you guys get to see how great my drawing skills are. So we're actually going to put this together as a process flow chart. Okay, and we're going to start whiteboard. Okay, so process flow chart can take many forms, but typically we just put them together, as a series of boxes with connecting arrows. So hopefully, here we go. This will work. So at the start of the process, we have this box. As you can see, my drawing skills are not the best. Okay, but this box here would be receiving, and that didn't quite fit into my where I wanted it to go, but you get the idea. The next box from there, and we're still on. So the next box, I'm thinking that this might not be going to. This is working completely different on the screen share than it did yesterday when you're not sharing your screen. Okay, this might be better. The next process is shot blasting. Okay. We'll put this underneath. Blasting. And then the next process is in here. I'm going to put blasting again, because this one here should have been scaling. And we've got that, fortunately, there doesn't seem to be much of a way to. So you guys will get to see me do struggle with this again. Scaling. Blasting. So that is essentially a not very good version of a process flowchart that describes visually the process. Right. So the raw steel comes in, it's received, goes through the scaling operation to remove mill scale, goes into a blasting operation where the wire is cleaned, goes into a drawing operation where the wire is drawn down to the appropriate size for processing. Once it's drawn, it goes into the coating tank where it gets coated with copper. From there, it comes out, it gets packed, and it gets shipped to the client. So from the essentially, the waste streams that we're going to be looking at are from this coating operation, and we have several waste streams that that occur. We have waste acid generation that is generated as a waste. We have process water. Which goes to wastewater treatment. And then from the wastewater treatment, we have it's a pretty small box. We have sludge generation or filter cake. And then we also have sewer discharges. And then one other that we have up here is air emissions. So by the time you're finished, this is an approximation of what your process flow chart should look like for this process, right? So we have steel receiving. The steel then goes into the descaling process, goes into the blasting process, goes through the drying process, into the coating tank. Out of the coating tank, gets packaged, then shipped to the customer. What we're going to be interested in is the waste products that are coming from this coating process. One of them being waste acid that gets generated, processed water that gets treated, and the associated sludge generation and sewer discharges with that. So the two waste streams that we have to characterize would be the waste acid and the sludge generation. Well, I'm glad somebody would say they would pay for this. They would pay for this art. So what I am going to do is I am going to attempt to get back to my whiteboard, which I appear to have lost. So let me just stop sharing for a sec, and then I will find it again. Yep, there it is. So what I will do is when we take the 10-minute break, I will show you an actual process flow chart that we prepare and we ship to the Ministry of the Environment. Well, I mean, I guess they would accept a hand sketched process flow chart like this. I'm pretty sure that they're usually used to seeing more professionally prepared ones, but that's essentially how you would prepare a process flow chart, and this is what a process flow chart for this particular process would look like. Okay, so let's go back to Okay, so we should now be back on to the PowerPoint presentation. So as I said, and as I actually showed you in that poor effort to draw a process flowchart, main manufacturing process, the sheathing of raw steel wires, shot blasting of the raw material to remove mill scale, drawing of the wire to the appropriate size, and the application of copper coating to the wire. Okay. This case study will focus on the waste generated during the copper coating process. After drawing, the welding wire is coated in one of 8 copper sulfate coating baths. So that is what actually occurs at the site. They have 8 production lines. Each one of those production lines is equipped with a copper sulfate coating bath. And as the wire passes through the copper coating bath, the wire becomes coated with copper. The important thing to realize in this particular process is that it is not an electroplating process. The copper is not plated onto the wire. It is actually a conversion coating process where iron is removed from the wire and is replaced with the deposition of copper. The baths contain a solution of copper sulfate, sulfuric acid, and water. The concentration of the copper sulfate and the sulfuric acid is 12 grams, or approximately 1.2% copper sulfate, 115 grams, or approximately 11.5% sulfuric acid, and the balance water for every liter of the bath solution. So that's the type of information that you need to know. You don't need to know it so much in order to characterize the waste. You just need to know what's in the waste. But it's certainly to calculate your actual releases for the National Pollutant Release Inventory. These concentrations are the type of information that you need to have. Okay. Waste generated from the copper coating process includes copper acid solution removed from the baths on a continuous basis to prevent the buildup of iron. So as I had mentioned, it's a conversion process. The copper essentially replaces iron on the surface of the wire. So that wire ends up in the coating bath and has to be removed. It actually gets removed as a sludge from the bottom of the tank. The wastes also include filter cake material generated from the treatment of water used in the process prior to discharge to the local sanitary sewer system, right? So those are 2 wastes that need to be characterized for disposal under Ontario Regulation 347. Other releases from the process that need to be quantified include sulfuric acid air emissions and copper discharge to the municipal sanitary sewer system. Those 2, the sulfuric acid air emissions and copper to the municipal sanitary sewer system, they need to be quantified for reporting to the National Pollutant Release Inventory. Okay. In order to characterize the sulfuric acid and copper sludge waste streams, we will use Figure 3 of the Registration Guidance Manual for generators of liquid and industrial hazardous waste. Right? You guys can either look at that link, which will take you directly to Figure 3, or you can we will use we'll use this version of it on the slides. But what is going to be a little less than ideal is I need to get these voiceovers off. Does anyone know how to get these voiceovers off of this? Somebody put in the chat once before how we do that. So just hold on 1 second. So we're just working at trying to get this. Okay. Aaron just showed me how to do it. I believe it was Aaron that showed me how to do this the last time that I ran into this problem. There we go. So the narration should now be off. So let's give this a try. Okay, perfect. So thanks for teaching me something there, Aaron. I'll have to keep that email around for use for future lectures. So essentially, this is figure 3. So you guys, as I say, you can either look at the figure 3 here on our screen, or you can go to that link that I sent you. So so first off, we will assess the sulfuric acid to determine the appropriate waste number and characterization for that waste stream. So this is what we know about the waste sulfuric acid. It has a pH of less than 2, so very corrosive. The waste sulfuric acid is removed as a sludge, so it's almost like a semi-liquid, but it would definitely meet the requirement of a liquid. Testing has shown that the sludge contains 0.2162% copper on a weight-to-weight basis. Testing has shown that the waste contains 5% sulfuric acid on a weight-to-weight basis. The facility shipped 50 shipments of acid sludge in 2020 for a total of 383,576 liters of acid sludge, and the acid sludge has a specific gravity of 1.47. So, significantly higher than 1, which we would typically see for water, and that's because even though the bath does contain a significant quantity of water, what is coming out in the sludge contains a lot of iron in a solid form, as well as sulfuric acid, which has a specific gravity significantly higher than water. Okay, so that is the information that we know about the waste acid material that's removed from the tanks on a daily basis and needs to be disposed of. All right, so we are going to attempt to go back. So this is the process that any person working in an industrial facility would go through in order to characterize this waste. Okay, so we start right here. Okay, and we simply move through the process. So the first question you come to, is the waste severely toxic? If it is severely toxic, it will get the characterization letter of S. There are very few industrial wastes that meet the requirement of severely toxic. The list of severely toxic materials are listed in Schedule 3 of the regulation, but it is fair to make the assumption in this case that no, it is not a severely toxic waste. So you then move to the next box. Is the waste pathological? Right. We have no body parts. We have no bloody bandages. We have no medical waste in there. So the answer to that is no. Is the waste a PCB waste as defined by Regulation 362? The answer to that again is no. There are no PCBs in that waste, and there's no opportunity for PCBs to enter that waste stream. Is the waste an acute hazardous waste chemical? So these are chemicals that are listed in Schedule 2, Part A of the of Regulation 347, and in this case, this waste does not contain any Schedule 2 Part A substances, so the answer is no. Is the waste a hazardous waste chemical? Okay, so these are chemicals that are listed in Schedule 2 Part B of the regulation. The answer to that is again no. Is the waste a hazardous industrial waste? So this hazardous industrial waste are wastes that are included in Schedule 1 of the regulations, and these are wastes that are essentially designated as a waste. So if we went to Schedule 1 and we saw on there waste acid solutions from coating operations, then it would be an H, or a hazardous industrial waste. But in this case, this waste is not listed in Schedule 1. Go to here. Is the waste ignitable, corrosive or reactive. We already know that the waste has a pH of less than 2, so it is in fact a corrosive waste. All right, so we at this point we select yes as a corrosive waste. We come back up. Is the waste leachate toxic? In this case, it is not leachate toxic. So the answer to that is no. And then we follow down through the rest. Does your waste have one or more of the hazardous waste characterizations? Yes, because we had selected that it was corrosive. This waste is a hazardous waste. The first characterization is the primary characterization. So we are now subject to generator registration requirements, and we have to ensure that we're registered through the H1 website, that the waste is registered, and that all fees are paid. So based on that, we know that our waste is a corrosive or it's a C class waste. Okay, from there we then use the Ontario waste classes that are found at this web link. So I'm going to just quickly share my screen. To that link so we can just take a quick look at it. If I can find that screen. And I don't seem to be able to locate that. I'm telling you, my goal for next semester is to be able to become much better at the use of Zoom. It's not an easy process sometimes, and this should be an easy process. It's just simply a jump to a screen that I cannot locate. There we go. Okay, so this is the website with the Ontario waste classes. So we go there and we look to see what our waste class is. So conveniently, the very first group of waste listed are acid solutions. So we need to pick out which one of these acid solutions would most fit our waste. And if you look at 112C, acid solution, sludges, and residues containing heavy metals. And examples of those are solutions of sulfuric acid containing copper, nickel, chromium, zinc, etc. So this waste clearly falls into the 122, the 112 waste class. So we have now successfully classified our waste as a 112C waste class. Okay, and essentially waste class 112 is selected, as I showed you there, because the waste is an acid solution. It is an acid solution containing heavy metals, because in our particular case, it is sulfuric acid containing copper, and copper being one of the heavy metals that is listed in that website. Okay. All right, for the waste acid sludge, the H1 public database for 2020 will show the following. It would show 50 shipments of 112C waste and a total 112C waste ship of 383,576 liters. So from going to the H1 site as a member of the public, that's what you would see. But it would you would not be able to determine what chemical constituents were in that waste that was released by the facility as part of shipping that waste material. In order to do that, you would have to go to the National Pollutant Release Inventory. So the very first question I ask here is reporting of the waste acid required to the National Pollutant Release Inventory? So the very first thing that we have to look at is the National Pollutant Release Inventory is set up so that you have to meet certain thresholds in order for your to have to report for individual chemicals. And I believe the last time I looked that there are 258 chemicals listed in the National Pollutant Release Inventory that require reporting. So if we were to look at Schedule 1A of the NPRI, you would see that it has the following reporting thresholds. Sulfuric acid, 10 tons MPO. Copper and its compounds, 10 tons MPO. So if your facility brings in if your facility manufactures, processes, or otherwise uses 10 tons or more of any one of those two substances, then you have triggered the requirement to report to the National Pollutant Release Inventory. So in 2020, the facility purchased 159.8 tons of sulfuric acid and 173.5 tons of copper. And I'm now asking the question that I just answered for you guys: has the reporting threshold for sulfuric acid and copper been met? And they have been, because those purchase quantities greatly exceed the 10-ton reporting threshold. The other thing that you have to look at is how did the facility use these materials in order to determine if you're manufacturing, processing, or otherwise using these materials. The facility does not actually manufacture sulfuric acid. It does not actually manufacture copper, so there is no manufacture going on, but it does process both of those substances as part of their MIG wire manufacturing process. So when in order to report these to the National Pollutant Release Inventory, you would report them as processed. Okay, so and we did look a little bit at that in the last assignment, where you could see facilities were reporting, whether they had manufactured or processed. It's still pretty tough to determine as a member of the public just by looking at it, exactly how it's used, but you can tell that this is a substance that's being processed. So it is substances that they are purchasing from suppliers and are then processing within their internal processes at the facility. Okay, so in order to report to the NPRI, we have to determine how much sulfuric acid and how much copper needs to be reported, because as we saw, the facility disposed of 383,576 liters of waste acid sludge, but not all of it contained sulfuric acid and copper. A lot of it was iron, and some of it would have actually could actually have been classified as just water. So what we do know about the acid is that or the sludge is that it contains, and this was listed in an earlier slide, it contains 5% sulfuric acid on a weight by weight basis and 0.2162% copper. So if you do that calculation, 383,576 liters multiplied by 1.47 kilograms per liter. That was the specific gravity or the density of the sludge, which will change the liters for us into kilograms. We multiply it by 5% sulfuric acid, and we see that we have 28,193 kilograms or 28.2 tons of sulfuric acid in that waste stream. When we come to copper, it's essentially the same calculation, except instead of 5%, we multiply by 0.2162% for copper, and we end up with 1,219 kilograms or 1.22 tons of copper in the waste stream. So you can see from these calculations that you need to be reporting to the National Pollutant Release Inventory that you released or that you disposed of 28.2 tons of sulfuric acid, 1.22 tons of copper. Okay. Sulfuric acid and copper were reported, as I mentioned, as processed or P. And the sulfuric acid and copper disposed of, a sulfuric acid sludge will be shown as being shipped for chemical treatment prior to disposal. I guess I could answer a question here. Why would we show this as being treated, undergoing chemical treatment prior to disposal? Why is that copper sulfuric acid sludge, why is it being treated prior to disposal? Anyone? Anyone? Don't even know if anyone's still awake. But why would we want to treat that? Why would we want to chemically treat the sludge before we dispose of it? Because we have to chemically treat it, you know, because we do have land disposal restriction requirements under Regulation 347 that need to be met, and there are substances within the sludge that fall under LDR requirements. In most cases, sulfuric acid wastes are also neutralized prior to final disposal, so they are shipped for chemical treatment prior to final disposal. Okay, all right. So it's coming up to 9 o'clock. Let's just take a quick 10-minute break, and then we will come back and continue from where we left off. Okay, so I'll see you guys in about at 10 minutes after 9. Okay, so we're back. When I made that very poor effort at sketching a process flow chart to you guys earlier, I'd said I would show you an example of a process flow chart that we have done. So I'm just going to share the screen for a second. So this is an actual process flow chart that we completed as part of an environmental compliance approval application. This process flow chart starts off as a very basic process flow chart, but as you can see, there's two separate processes. The top one says C sheet 2, the bottom one says sheet 3. So if we move to sheet 2, we see this horribly complex, let me see if I can get that all on the screen for you guys. You can see this complex process flow chart, and this flow chart lays out every step of the process. In this particular instance, the process is involved in reconditioning a steel drum prior to using it. So so you can see they can get fairly complex. They can get you know, fairly busy. This one is put together so that review engineer can look at this and get a good handle on where air emissions are coming from within the process, and then can go back into our environmental compliance approval application and just be sure that we have every one of these air emissions accounted for in our application. And this is the second process that they have at that site. So as you can see, I mean, there can be a fair bit of work in putting together these process flow charts. And one of the keys to putting together a process flow chart is to, you really need to be able to understand the process that you're trying to visually describe within the chart. And some flow charts that are used for you know, a chemical process purposes can be even more complex than this. They can get right into, what temperature is at each point in the process, and, chemical reactions that may be taking place. So even though this process flow chart looks like it's fairly busy, it could actually be taken to another level, and show even more information on it. So that's process flow chart. It is probably something that you should spend a little bit of time looking at how you put them together. This was an environmental compliance approval application that took us almost 3 months to put together. And as you can see up here in the document, there's 955 pages that go along with this. Yeah, would we sit down with the process engineer? Yeah, we would sit. So when we put together a process flow chart like this, every one of our ECA applications has a process flow chart along with them, because it's actually a requirement under the regulation that we provide one. So we sit down with process engineers, maintenance personnel, plant operators. Believe it or not, if you look at this, process flow chart, this particular facility does not have a process engineer. So we were typically dealing with process operators, facility maintenance people in order to put this together. So something like this gets put together, and it generally goes backwards and forwards to the client numerous times to make sure that we actually have this right before it gets included in any document that is going to be shipped to a government official, because you need to ensure that that it's accurate. And this is the people who work for my company. This is something that we tend to find that they struggle with, even in the most basic process flow charts. I'm just if I can quickly, I know that I'm digressing a little bit here, but if I can quickly, I'm just going to quickly see if I can pull up what I would classify as a simple process flow chart. See if that's even something that I can quickly locate. And it doesn't look like I'm going to be able to locate a simpler version. So this is a very simple process flow chart for a simple company that we did an environmental compliance approval for. And as you can see, it's very basic. There's not much going on at this facility, but we find, as I mentioned, we find that new employees really struggle with the concept of process flow diagrams, and really where they struggle is essentially where do they start, right? I always tell people doing these for the first time, you start at the beginning. You just go to the beginning of the of that plant where they receive the materials, and you just walk through the process. And gradually over time, people get better. But as I say, new employees do actually they struggle quite a bit with this concept of process flow charts. Okay, so let's go back to our PowerPoint presentation. So this is where we left off, where we had calculated copper and sulfuric acid releases for the MPRI within the waste sulfuric acid sludge that is generated from this facility, right? But as part of the MPRI, once you've triggered the reporting threshold, which this facility clearly has, you must, after that point in time, quantify and report all releases of that substance. So essentially, no matter how small the releases are, you have to identify them, and then you have to quantify them, right? So at this facility, in addition to be disposed of as waste, sulfuric acid is released to the atmosphere. And as I just said, because the threshold for sulfuric acid has been tripped, all releases of sulfuric acid must be reported. And we're now going to take a look at an example of how sulfuric acid releases to the atmosphere are calculated and then reported to the MPRI. Okay, sulfuric acid emissions. Skip the slide. Yep. So these are the key things that you need to know about sulfuric acid air emissions from this facility. So sulfuric acid emissions from the copper coating tanks are controlled using a packed bed scrubber with an efficiency of 98%. I think I mentioned this in one of our earlier lectures, is that yes, you can control emissions from process lines, process equipment, but no control equipment is 100% efficient. So in this case, this packed bed scrubber has a rated efficiency of 98% for the removal of sulfuric acid emission. The packed bed scrubber has a volumetric flow rate of 11.33 cubic meters per second. So when we talk about volumetric flow rate, that is just the amount of air or I should actually say the amount of gas that is being taken into this scrubber unit and then discharged out the exhaust stack to the atmosphere. So that discharge rate or volumetric flow rate is 11.33 cubic meters per second. The inlet loading of sulfuric acid to the scrubber is 3.74 milligrams per cubic meter. That was determined through loading testing that was done. Some of the environmental students have been working with us on doing stack testing or source testing. We're in that instance, we're source testing after the scrubber unit to determine, we're not interested in the removal efficiency of the scrubber unit. We're just looking at how much of the contaminant is actually being discharged to the atmosphere. But in this particular case, the loading to the scrubber was actually tested to ensure that the scrubber design would effectively remove sulfuric acid to levels that they can then discharge to the atmosphere. And then the other key piece of information is scrubber unit operates for 6,132 hours per year. I should say it doesn't operate exactly that number of hours every year. That's how many hours this particular unit operated in 2020. So we've got an efficiency of 98%, flow rate of 11.33 cubic meters per second, a loading to the scrubber of 3.74 milligrams per cubic meter, and an operating time period of 6,132 hours per year. So we take all of that and we then calculate it as follows: 3.74 milligrams per cubic meter multiplied by 11.33 cubic meters per second multiplied by 1 minus 0.98 equals 0.85 milligrams per second are being released to the atmosphere. That in brackets there, 1 minus 0.98, that takes into account the efficiency of the scrubber unit in reducing that inlet loading of 3.74 milligrams per cubic meter. So this This scrubber unit is releasing 0.85 milligrams per second. 8.5 milligrams per second multiplied by 1 kilogram has 1 million milligrams, multiplied by 3,600 seconds per hour, multiplied by 6,130 hours per year, gives you 18.76 kilograms per year, or essentially 0.019 tons of sulfuric acid that is discharged to the atmosphere. So you can look at that, 8.76 kilograms of sulfuric acid released to the atmosphere over a year. You know, it's not a large amount of sulfuric acid, but it has to be quantified and it has to be reported to the MPRI. And you saw some of those reports where, you know, you were looking at facilities and they were showing discharges, particularly of solvents, to the atmosphere. So in this case, if a member of the public went and looked at this MPRI report, they would see that this facility in 2020 released 18.76 kilograms of sulfuric acid to the atmosphere. Okay, so we will now look at the copper sludge, and we're going to look at the copper treatment sludge from both the regulation 347 perspective and also from an MPRI perspective. I just want to, do you guys have any thoughts? So let me just go through the some of the parameters of this first, right? But essentially, copper sludge is generated from the wastewater treatment system, which removes copper from effluent prior to discharge to the sanitary sewer system by metal hydroxide precipitation. The effluent that comes from the copper coating line is essentially water that's used to rinse the wire as it exits the copper coating tank. Because it's rinsing wire that contains some of the tank solution, you do end up with significant amount of copper in the effluent that's entering the wastewater treatment system. The city of Toronto has a limit of, I believe it's 2 milligrams per liter of copper on the discharge side. So they have to reduce the copper concentration to within the sewer use bylaw limit. That's done by essentially raising the pH of the effluent. They add caustic or sodium hydroxide. The copper precipitates out at that pH, at a pH of about 10 as copper hydroxide, and that precipitate is then processed through a filter press, which compacts it into a sludge material that is then disposed of. So sampling of the sludge revealed the following. So this sampling was all done in 2020. The average moisture content was 78%. Average copper content of was 10% on a dry basis. The sludge had a total slump of 57 millimeters. The sludge has a pH of 8.3. The sludge was tested through T-clip testing, and all contaminants were below the leachate standards of regulation 347. So I have a question for you guys, and I think I can see most of you. Would you suspect that this material is a waste under regulation 347? Anyone have any thoughts? So if you think that this is a waste under regulation 347, maybe stick your hands up and we'll take a look. Anyone? So a bunch of you are raising your hands. So you know, obviously believing that this would be a waste under regulation 347. I mean, when you look at the process and you look, you look at the fact that this has an average concentration of copper, of 10%, which is a heavy metal, you would certainly expect this to be a waste under regulation 347. But as is with every waste, that is generated at an industrial facility, that waste needs to be characterized by someone, whether it's an external consultant, their waste carrier, or a chemical engineering technologist or environmental technologist that works for the facility. Somebody needs to sit down and then characterize this waste. So again, that's done through figure 3 of the waste generators guidance manual. So again, we're going to take a look at this, and we are going to, from the start process, we're going to go up. Is the waste severely toxic? No, because there is no components from Schedule 3 in there. Is the waste pathological? No, it didn't originate from a dentist's office. There is no pathical waste in there, so that's a no. Is the waste a PCB waste? There are no PCBs in the waste, and there's no potential for it to be contaminated by PCBs. Is the waste an acute hazardous waste chemical? There's no components in there that are in Schedule 2 Part A, so that becomes no. Is the waste a hazardous waste chemical? There are no Schedule 2 Part B components. Is the waste a hazardous industrial waste? There are no. It is not listed under Schedule 1 of the regulation. Now, interestingly, if you were to look at Schedule 1, you would notice a waste that's listed there. And I don't know the exact wording that's used, but it's along the lines of wastewater treatment sludge generated from zinc electroplating of carbon steel, or from coating of carbon steel. So I mean, potentially it could be, but it doesn't meet that definition exactly. So the answer to that as well is no. Is this waste ignitable, corrosive, or reactive? Well, the pH was checked. It was, I believe we said it was 8.5. So the answer to that is no. Is the waste leachate toxic? So we have to look at the criteria on Schedule 4. We indicated that all contaminants were below the levels of Schedule 4. So the answer to that is no. So as you can see, we've came through that whole top process, and we have not been able to assign a waste characteristic to it. Does your waste have one or more hazardous waste characterizations? In actual fact, in this example, it's no. So we move to here. Is the waste decharacterized waste with untreated UHCs? In this case, it's not, because there's been no treatment of the waste to reduce hazardous waste constituents, so it has not been decharacterized. So we follow through here. Is this waste a liquid industrial waste? So we said it had a slump of, let me just see what the slump was. It had a slump of 57 millimeters. That is below 150 millimeters. So is this a liquid industrial waste? The answer to that is no. So we have came through the whole process, and this waste is actually not subject to waste generation and registration is not required. So having followed through this the flow chart, we have determined that this is not a hazardous waste, and we can dispose of this waste outside Regulation 347. So exactly. So Aaron just said, so transporting that bulk sludge for refinement does not need to be tracked by HWIN. So a member of the public would not see this waste on the HWIN public database, because it's not subject to Regulation 347, right? So as we've said here, there, and as I explained, it does not require disposal under Regulation 347. So this facility is perfectly within the law to take the sludge, put it into a waste bin, and that waste bin could be picked up and taken to any non-hazardous waste landfill in Ontario and disposed of as a non-hazardous waste. And part of the reason of why that is if you go to the leachate standards in Schedule 4, you'll notice that copper is not one of the leachate parameters. So even if copper leaches from this waste in significant concentrations, it's not on the schedule, so it's not a leachate toxic waste. And then Aaron said, I'm sure they want to recover the copper, though, considering its value. And that is one of the things that any of these wastewater treatment sludges that come from a process that contains significant quantities of a metal that has significant value is generally sent for redefinement to recover that metal. So in this case, as it says here, the sludge is shipped from the site on a general bill of lading. So it's not shipped on a Regulation 347 manifest, and it's shipped for the recovery of the copper content. The sludge shipment will not appear on HWIN public database, so no one would see that this waste is actually being generated if they were to look only there. All right. For MPRI reporting, the copper content can now be calculated as follows, because we know that we have 57,190 kilograms generated per year. We multiply that by 1 minus 0.78 because the sludge contains 78% moisture. There is only actually 28% dry sludge present. So your 57,190 kilograms per year becomes 12,582 kilograms of dry sludge shipped per year on a dry basis, right? 12,582 kilograms per year multiplied by 10% copper equals 1,258 kilograms or 1.26 tons of copper shipped per year. There's a couple of things that this facility is looking at doing, and that is how can they make the wastewater treatment operation more efficient, so more of the copper ends up in the sludge, and also how can they reduce this 78% moisture content, because I don't know if somebody wants to quickly do the math, but you're shipping 57 tons, of which only 12 tons of it is actual sludge. So you're looking at 37, so over 40 tons of the material that you're actually shipping as sludge. And 45 tons of it is water, and unfortunately, there's a certain tonnage fee for the shipping and disposal of that material. So wherever possible, you want to significantly minimize the amount of water that's generated in the sludge. And this 78% water content is fairly that's fairly common for what we see with a standard filter press. We usually see moisture contents from 60 to 80%, but even with those high levels of copper, you will I just got sidetracked there, so yeah, so you want, so even with those high levels of moisture, interestingly, typically sludge will generally always pass a slump test. The filter press does form it into enough of a solid that it will be well below the 150 millimeters that is the cutoff limit for what would make this a liquid industrial waste. So as it says at the bottom, a release of 1.26 tons of copper will be reported to the MPRI, and the disposal method being indicated as metal recovery. And we did see some of that in some of the assignment we did where we looked at the waste disposal from A.G. Simpson. We could see that material was going for metal recovery. So that tells us, if we're looking at these reports, that this facility is shipping a particular waste material to a refiner to recover the heavy metals. Okay, so but as we have already stated, because we triggered the requirement for reporting of copper to the National Pollutant Release Inventory, we have to quantify and report all releases. So in conjunction with the wastewater treatment sludge, like all types of processes, the wastewater treatment process is not 100% efficient. Some copper does remain in the effluent, and that copper gets discharged to the local sanitary sewer system. So in this case, the average copper concentration in the effluent discharge is 0.2 milligrams per liter, or 0.2 grams per cubic meter of effluent. The facility discharged 23,765 cubic meters of effluent in 2020. The amount of copper discharged to the municipal sewage treatment plant is then 0.2 grams per cubic meter, multiplied by 23,765 cubic meters per year, multiplied by 1 kilogram is 1,000 grams, equals 4.8 kilograms of copper discharged to the municipal sewage treatment plant. So again, a fairly small amount that is being released, but it does need to be quantified and reported to the ministry, or to the MPRI, and this would be shown as a release to a sewage treatment plant. And then if you went digging into the report, that you would actually be able to locate within the report which sewage treatment plant that was discharged to. So if you looked at this particular facility's report, you would see that this facility discharged it to the Highland Creek municipal sewage treatment plant in Toronto. So that is essentially an example of how wastes are generated from industrial facilities, and then also how the wastes are calculated, the volumes that are calculated, how the individual constituents are determined and calculated for their release amounts, and then how we would go into the reporting of those to the National Pollutant Release Inventory. So I mean, it's a fairly good example, because it does show that even though you get wastes being generated from industrial processes, not all of them meet the requirements of Ontario Regulation 347. Most facilities do ensure that those type of wastes are disposed of, in an environment as an environmentally friendly manner as possible. We have had several instances where the Ministry of the Environment has been monitoring wastes coming into landfills, and when they identify wastes that clearly come from an industrial facility, so waste, for example, is a wastewater treatment sludge, and we had an actual case of this from a facility in Peterborough where the Ministry of the Environment was at a site when a load of their sludge was disposed of, and they went to the site, and they wanted to see all the documentation of how they characterized the waste and how they came to the determination that it was a non-hazardous waste, and they were able to show that documentation, and of course the ministry went on the merry way, and there was no notice of violation issued, or any penalties subject to that waste disposal. So that's an example. Does anyone have any questions? Everyone has a good understanding of how all those calculations were done? Yes? Everyone's okay if they see some of those calculations appear on the next test. Yep, so it sounds like everyone thinks it's fairly straightforward. And the calculations are fairly straightforward. What's more important is an understanding of the process and how the material is generated, and how you get to the actual releases that you calculated, because you can't just walk into a wastewater treatment plant, look at effluent sludge and say, oh, this is going to contain X amount of whatever. There's a significant amount of testing that needs to be done, and those test results need to be assessed, and then the calculations actually need to be done. And when you're doing those calculations, one of the important things to remember is that the labs always report the concentrations. So when you're doing an analysis for metal, they always report the concentration as a dry basis, but they will not always report the moisture content of the sample that they tested. So the two pieces of information are equally important and go hand in hand, and you must have both of them in order to be able to do the calculations. Because if you don't know the moisture content, then you have to assume that the concentration reported to the lab is reflective of the entire sludge sample, moisture content included. You would significantly overestimate your releases of your metal for the National Pollutant Release Inventory. Okay, so anyone have any questions? I actually didn't think we would get through this in our 2-hour period, but here we are with 15 minutes to spare, and we are done. Any questions on anything to do with the course at this point in time? Everyone good? I'm going to see the environmental students at noon today. If it's not raining, you guys are going to be collecting a sample from one of the groundwater wells. If it is raining, we may look at jumping ahead to Lab 3D. But I looked outside during our break there, and it wasn't raining, so hopefully you guys will be able to go and get a sample from one of the monitoring wells. Okay, all right, so thanks for everyone for attending. We actually built up a fairly sizable audience for this lecture. We started off with 4 at the beginning, but people did start to connect as we progressed through. So thanks everyone for attending, and I will see you either at the lab this afternoon or at the next lecture next Thursday. Yes, you will need your lab coats, because once you have that groundwater sample, you will be bringing it back to the lab and you will be doing some testing on it. Okay, all right. Everyone good? Okay, thanks guys.